Hello and welcome to How to R. This is Mike and we're going to talk about data visualization. Data visualization is something that R is actually very good at doing and has actually been used by the New York Times, by Facebook, and by Twitter for some pretty impressive graphics. So I'm sure if you do a little bit of Googling you can see those. So today we're going to be working with the iris dataset again, and it's actually built into R. So we're just going to hit data iris, and that will load it for us. Alright, so let's just look at iris just to remind ourselves of what it is. It's got the lengths and widths of petals and sepals, and then the species. And we're going to go ahead and going to name the sepal length SL like before. So type in iris, $, and then you can use a tab to find it and autocomplete there. Alright, we'll go ahead and do that. Alright, so the first graphic we're going to make is a histogram, and that function is just hist, H-I-S-T, parentheses, and then put in your object. And there you go. There's your histogram. So you can also do what's called a density plot using the function density. And you hit density and then the object SL. And what it does is it shows you the output here. And so you actually should name it density SL. We'll call it D, or let's say SL.D. Alright, so density SL, and then you hit plot D. Not D, SL.D, okay? Alright, and there you go, it shows you the density. Now what if you want to use this density over the histogram? How would you do that? Well, what you do is you go ahead and plot the histogram, and then you can use the function called lines and do that. Now, there's going to be an error here. Well, it doesn't show an error, but why in the world is it so? See that little mound right there? That's supposed to be the density plot, but it's nothing like the histogram. So what's going on? Well, I'll tell you what it is. If you look at, let's look at the help file for density. There's yes, not density, excuse me, hist. What we did is we used frequency instead of probabilities. Whoops. So if you look at the plot, let's look at the plot. Notice these are frequency. So how many times was something between 5.5 and 6? Well, it was done 30 times. So the solution is that you set frequency to false. So frequency is FREQ equals false. Now let's try that again, okay? So let's run it again. Now notice the bars are the same shape, but now the scale has changed, right? So now it's from 0 to 1 because it is a probability histogram. And now let's try lines again. And there you go, just like expected. A nice density there. Alrighty. So, how else can we visualize our data? There's something called the boxplot. And the function is just boxplot with parentheses. Put in your object, SL, and it makes a boxplot. So these are called whiskers here. This is the median, and this is the interquartile range. And if it had outliers, it would actually have dots on the outside. And the default is that the whiskers are 1.5 times the interquartile range. And so if anything is beyond that, it considers that an outlier. So you can actually name graphics objects. So let's call this sl.b Okay, run them again and name it. And let's look at some of the things that are in that. Sometimes it helps just to look around. So let's see if the summary gives us anything. Summary of SL.B. Well, looks like there are some things here. There's something called stats. It has junk in it. In, conf, out, group. Okay, so there's something in there. Let's see if we can learn a little bit more. Okay, so those are the names. So if it's named, remember you can access named objects. So let's do a little exploring and look at the function boxplot. Alright? So the arguments are here and the value. So if you look at value, this tells you what it returns. So details will explain a little bit about it, and then the value explains the actual things that it will return when you put something in. So stats is a matrix where the column contains the extreme of the lower whisker, the lower hinge, the median, the upper hinge, and extreme of the upper whisker for one group or plot. We only put in a vector, so it's only going to show us that one. Alright, so what that means is stats can give us the value of each of these things. And there are 1, 2, 3, 4, 5. And we saw here that it had length 5. So let's see. Looks like the order is extreme of the lower whisker, then the lower hinge, and the hinge is this right here, upper hinge, lower hinge. Alright, and then, yeah, so like let's say you want to see what the upper hinge value was. You can do sl.b, because we named it, and then remember the name, you can access names using the $sign. Alright, and then let's see what that does. Hit tab, stats, okay, and we know there are 5 objects, so let's go ahead and see what that looks like. I'm going to hit Command Enter. Here's the lower whisker, the lower hinge, the median, the upper hinge, and upper whisker. So if you want to just access one of them, you can do that by indexing through that vector. It's a matrix, but because it's a single column, it's also a vector. So let's stats, and let's say we want to look at the median. Alright, so we do the third one. Alright, and there you go, 5.8. Or what if we want to do the upper whisker? That's going to be, what, the 5th one, so 5. There you go, 7.9. So that's how you can access things through the boxplot. Very nice. Alright, so now another kind of graphic is a bar plot. So let's put bar plot, and there you go, there's a bar plot. Now how is this different from a histogram? Well, a bar plot just takes the data as is and just plots it, right? A histogram bends it nicely. So there you go. And we can actually learn a little bit more about bar plot by looking at it here. Yeah, there we go. Yeah, that's it. It's pretty simple, and you know, I don't use it quite that often. I use histogram typically, but sometimes you might need to use it for something. All right, another one is a scatterplot matrix, and it's created using the function pairs. So hit pairs, and then their parentheses, and then it's a scatterplot matrix, which means you're going to have scatterplots of variables against one another. So we're going to be in the iris data set, all right, and then we're indexing, so we're going to go ahead and hit our square brackets, and then because it's two-dimensional, we're going to use a comma, and then we want to see the first 4 columns. So you can do 1 through 4 like that, and see what happens. There you go. So sepal length, sepal width, petal length. So what this is now you can visualize the relationship between each variable. Now if you look here, there seems to be a very strong positive linear relationship between petal length and petal width. Kind of makes sense, right? It's not quite as strong between sepal length and sepal width. You know, it's sort of cloudy and not really clear here. And what's interesting here is this is vertical, while this does have a seemingly a nice one-to-one relationship. Not exactly, but there's definitely a difference between these two. So anyway, you can get a nice idea of what's happening here. You can see very strong relationship here. And notice also this interesting clustering. You know, one would probably guess that this is divided by species, but you know, we can look at that in further detail. Let's actually see what happens if we look at all 5. Okay, there you go. Now you can see the clustering. Right, so this is one species, this is the second, this is the third. And these are categorical variables, remember, but you can still see relationship. I mean, the different species have, you can see this one tends to have a width in here, this one in here, and this one here. So there's definitely some stuff going on here. So you can kind of explore relationships. All right. Now, let's just, before we move on, let's see if we can understand a little bit about the distribution of the sepal length, especially comparing it to a normal distribution, and that is done using a qqplot, and it's called qqnorm, and you put in SL, and this is a qqplot, and what it does is, you see the axes here, it uses the range of the data to create the ideal. Well, it plots it on the scale of the ideal, or I guess a Gaussian distribution. So let me, for clarity, the next function we're going to use is qqline. It's going to put a line in here, SL. And if things are on this line, that means that they would be perfectly Gaussian, right? They'd be completely distributed Gaussian or normal. And you see this is called theoretical quantiles, and that's what it means. If it strays from that too far, that means it's probably not distributed Gaussian. And Gaussian is just another way of saying normal. Normal can kind of confuse if just because we use it a lot in other ways. Anyway, so this is a way to test normality. If this is over here, it's kind of straying a little bit. That might be acceptable because it is far out in the tail, but you'd want to do a little more analysis to check that. Alrighty, so now we're going to show a cool feature where what if we want to look at a bunch of plots all at once? Well, there's a graphics parameter called, and you use par. It's a function, and that means parameter. That's short for parameters, and it's how you change graphics parameters. So this is the graphics. This is the graphics device. And what if we wanted to use see 4 graphics at once? The option for that is within the function par, you set mfrow, and that stands for, let's look at the function par, and then you can search within this topic here, mfrow, and see what that does. Okay. It's a vector, so you're supposed to enter in a vector. The first one is the first entry in the vector is the number of rows, the second is the number of columns. And the figures after this is set will be drawn in a basic matrix. Okay? So that's what it does. So let's set this equal to, and we want a 2 by 2 grid. So C 2 2. Alright? So it doesn't look like anything's happened. But let's go ahead and let's take some of these things we've done before, and we're going to use this. Alright, so we're going to copy that here. And let's look at the boxplot. Oops. Okay, we're going to copy boxplot down here. So that's 2. And let's look at the qqplot. And let's do the bar plot too, why not? Where'd that go? There we go, bar plot. Okay. So notice we have 4 different plots. We've already set the parameters, so let's just run these plots and see what happens. There you go. So now we have a 2 by 2 grid. There's a histogram with a density overlay, a box plot, the qqplot, and the bar plot, all in one. So that's a really great function to know, and you can reset it. So the default mfrow parameter is just a 1 by 1 grid. So it'd be mfrow, so parameter mfrow equals, and then you make a vector c1, 1. You can reset it. And so if we were to do that again, let's say we do the histogram and the density together, see it's back to 1. So you can change that back and forth. Alright, so now we're going to do a couple of advanced graphics, and to do that we need to load the lattice package. So you hit library, and then you can quote or unquote actually. Let's see. No, oopsie. It's always a good idea to quote it, but R is pretty forgiving on this one, if you want to just do that. Okay, so load the lattice package, and if you haven't gotten it yet, you can go to Packages, Install Packages, alright, and then search for lattice. It shows up there, and then you click it, and then you do want to install dependencies, and then click Install, and it'll download it for you and install it. And then you can load it by using library. Okay, so I already loaded it. So we're going to go ahead, and the function we're going to use in the lattice package is bwplot, and that is a box and whiskers plot. Alright, and it uses the formula interface, and so, which means that you will specify the data to draw from later, and so you can use the names of the variables directly, like this. So sepal length, and then you're going to graph that, plot it against, let's just say, sepal width. Alright, and then, so that's the x there. And the data we're going to use is just iris. So it will know to look in iris for the variables with these names. That's just how this function happens to work. Alright, let's look what happens. There we go, a box and whiskers plot. So this is sepal width, and notice, excuse me, for each value of sepal length, it gives you the box plot of sepal width. And so if you wanted to switch these, you just switch them here, and it'll show you the other way. Okay, and this is a tilde here. Excuse me. It's a tilde, and that's part of the formula. That lets it know to plot this against that. So let's do this one. And there we go. So for each sepal width, this is the sepal length. Alright, that's useful for kind of seeing how things change across values of another variable. Alright, another plot is a dot plot, and that uses the same interface. So we're just going to copy this right here. So the options are the same for this. And it's just another way now you can just see the actual values. So where they are, whereas the box and whisker plot showed you the range, the dot plot will just show you where they are. Alright, another one is the XY plot, and that uses the same interface as well, except in this case you can condition on another variable. So for example, let's say show us the sepal width by sepal length given, say, and this uses the I forget what that's called. It's just a straight up thing. I don't remember what it's called. Let's say petal width. Alright, it's going to take a minute, kind of has to think about it. And so now you have a conditional plot where you can look at, let's do by species. I think that'd be more interesting. Okay, so I'm entering species. Alright. So now we've conditioned on the species and are looking at the sepal width and sepal length in each. So this is sepal width against sepal length within each species. But you could do it on a numeric plot as well. As you saw, it just gave you more of them. So now you can see, oh, okay, the relationship here is much stronger in the Setosa species than it is in the Virginica species, and even the versicolor. So that's some interesting information you can get from that plot. Alright, and I'm going to show you one more really cool plot, and it's in this psych library. So you load that using library and then psych, P-S-Y-C-H. And if you haven't downloaded that package, then go to packages and install packages and do that and then load it. Alright, so this function is called pairs.panels, and we're just going to do iris, and then let's just do all of iris. Let's do the whole thing. Alright, this is really a cool graphic because it gives us a lot of information all at once. It's very data rich. They even change the size of the numbers. So these are correlations here between the variables. They change the size based on the magnitude of the correlation. So if it has a stronger correlation, it has a larger number. Pretty cool. You know, it works well with our human psychology. It makes histograms so you can see the shape of the distributions, and we see that the petal length is bimodal and petal width as well. And it also gives you the scatterplots, and here by default it has these correlation ellipses. You know, I've never really studied those, but I'm guessing it's supposed to give you an idea of how strong the linear relationship is. And you can also, you have the lines, the low S curves that go through and kind of show you the shape or of the data. So that's a very cool plot, and there are options you can change about it. For instance, you know, whether you should draw the low S smoothing lines, whether you want to actually have the ellipses. So we could set that to false and then plot it and see they're gone. So, and you can change the colors of things too. Like I'm not a big fan of this for the histogram, but anyway. All right. So one more thing. Let's suppose you want to source. Let's say you have a bunch of graphics that you want to just make again, and you don't want to have to run all the code again. Well, I happen to have created one. I call it my plot, and I'm going to open it. Notice I clicked on this in the file browser, and it opened it here. And so what I've done is I've loaded the iris data, and I create the variable like that, and then I make a bunch of these plots like we just talked about, and that's what it does. But let's say I know I'm going to look at that again, and I don't want to have to go in there and go to the actual file. It doesn't have to be open. It just has to be in the same directory that we're in, unless you write a path to it. So let's source, and then I called it myplot.r. And see what happens. It creates a bunch of plots. Okay? And these are all... I'm going to clear all the things just so you can see that these are actually new. Okay, so I just cleared them, and I'm going to source it again. So there are no plots. There's nothing to go through. And what happens? I hit source my plot, and boom. It runs all the code in that file, and the code in that file I told it to make these different plots. So there we go. And that's how you can use source. Source just says run the code in this file, and so it does. Alright, so that concludes our data visualization discussion. If you have any questions or comments, please feel free to let me know and comment, and yeah, we'll go over some more fun R stuff in a new video. Alright.